So good afternoon and welcome to the lecture today. As you could see on the title slide today, we're in week 8. So this is going to be one of the last lectures we have for calculus. Today, 2 times 45 minutes like usual. And also Wednesday morning. Don't forget, on Wednesday morning you also have your tutor meeting. So this will be your last tutor meeting before the test. A bit of organizational stuff and what I will be doing today. First of all, don't forget that on Thursday is the resit for the STAR test. So if you didn't pass the STAR test or you would like to improve your result, you can do that on Thursday. That's going to be Thursday evening and the link is on Canvas. You will find all the necessary information there. Then today what I would like to do is first deal with the questions that people send me by email. So that's a couple of questions from the homework, from the online tests, some integrals that people didn't manage to do, so I'll discuss those. I'll go through the questions that have been put on Canvas as usual. And of course there is also a bit of week 7 material that is still left. Now, if I still have time after all that, I also have additional questions, so there is also extra exercises, and I'll go through those extra exercises basically after all the other stuff. So in principle, this week is exam preparation, and as such, I will be answering all your questions. So please let me know if you find any difficulties, and that can be either in the homework, it can be in the online test. Maybe you've looked at the old exams that we put up on Canvas. On Canvas you can find the final exams plus the resit exams from last year and the year before. So you have 2 years of tests to practice with. And if you have any difficulties with that, we provided solutions, but still if you think something is unclear, I'm happy to do them here. Just let me know. So probably the best way to do that is to use Canvas, the questions of the week that I will go through in a minute. You can also put the questions there. You can put them now if you ran into any difficulties, and I will look in the break and see what I can do in the second hour. And also if you're going to work on calculus tomorrow, please post them and then I'll address all your questions on Wednesday morning. So outline for today, let's start with the bit of material from week 7 that we didn't finish. So let me go to the slides 2. Here you see the slides, and let me go one back. So we talked last week about arc length and surface area. Well, we covered those on Monday and I finished them on Wednesday, so I will not be talking about those anymore. We also talked about differential equations. And differential equations, there are still a little bit left on the logistic growth model. So I'll quickly go through what we have seen last week on differential equations. And then I'll finish the topic and then I'll move on to your questions. So let's see. Last week, when talking about differential equations, I started off with a couple of applications. I tried to convey to you the message that differential equations are very important and they show up in a number of applications. So in various areas of science you see them appearing. One of them is the gravitational laws that Newton came up with, and they basically they tell us how the planets, for instance, in our solar system move with regard to each other. If you have 2 masses, they attract. The attraction depends on the individual masses. So if you have larger bodies, masses M1, M2, if they are bigger, then they pull stronger. So the sun in our solar system has the largest mass and that pulls strongest. And then it is divided by the distance squared. So the further away, you don't feel it anymore. So as we said, Newton did a couple of basic experiments basically and came up with this formula. And it appears that this is incredibly accurate, surprisingly accurate, more accurate than you could really expect from the observations made. And with these laws, I told you that you can write down a couple of differential equations. So here is a set of differential equations. So not one, as we have seen in the exercises and as we will be solving ourselves during calculus, but a system of them. So basically for every planet that you would like to include in your solar system, you will have a position and you will have its momentum. So momentum is velocity, mass times velocity. So basically one planet gives 6 unknowns. X, Y, Z position, so that's 3 unknowns, plus X, Y, Z velocity or momentum. So with each planet that you would like to add to your solar system, if you want to do simulations, you get 6 more equations and 6 more unknowns. So here is something where we have the Sun plus 5 additional planets. So basically we have 5 times 6 is a system of 30 equations to solve. If you do that numerically, because this is too hard to do analytically, you can use numerical methods, and I told you you don't have to know this for the exam. This is a bit of background knowledge. If you use different numerical methods like Euler forward, Euler backward, or the midpoint rule, you get different numerical results, and it's immediately clear from the pictures that I show you here that here you should be using the midpoint rule, or at least a numerical method that has similar properties so that conserves the orbit of the planets. Another application we looked at is a pendulum. So if you have a mass and that hangs on a piece of rope and you make it swing, you can also describe that motion by using a differential equation. So in this differential equation there is a second derivative. We don't deal with them during this course. If you're interested, you can join more advanced mathematical courses where it is being shown how you can deal with this. But what I showed you, I'm not going to play the movie again, but you can do that yourself, is that if you do an experiment or if you do a numerical simulation, that you get similar results or even the same results if you know the exact parameters in the experiment. And with numerical simulations, you can play around. So you can vary the number of masses, you can vary the length of the ropes, and so on. Then we moved on last week to look at a couple of simple differential equations that we can actually solve using pen and paper. So we can find analytical solutions for that. So analytical solutions are exact solutions, pen and paper solutions. And we have seen that we can use integration techniques that we have studied to solve these differential equations. So one of them was bacterial growth that you see here. So it is described by y prime equals k times y. So y is the population size. So how many bacteria do we have at any moment in time? So the idea is that at some time 0, when we start our experiment, we know the number of bacteria. And then after that time 0, we would like to describe how many bacteria we have at any moment in time. And last week we solved this and we have seen that you get exponential growth. So you get something like a constant times e to the power k times t, where k is the growth constant. It describes how fast the bacterial population will grow, and t is time. And we also studied this second model, which was Newton's law of cooling, which is basically if you have a cup of coffee that is hot and you put it in a room, then if you wait sufficiently long, it's going to assume the ambient temperature. So the temperature of the coffee will go down to to room temperature, say 20 degrees Celsius. And we have seen that also this differential equation we can also solve. Both of these equations, so both bacterial growth and Newton's law of cooling, lead to a differential equation that we can separate. So basically we can move all the y dependence to one side of the equation and all the t time dependence to the other side of the equation, and then we can integrate both sides separately. So then we're basically back into the week 6 material where we looked at integration and how you can do that. So this is a quick overview of what it looks like. So this is the general outline. If you have a differential equation, it usually has this form. So y prime is given as some expression that involves t and y. And then the idea is that you can write everything with y to the left, everything with t to the right, and you integrate both sides of the equation separately. We will do examples also today, since a couple of you have asked for examples on integration, and I will also be looking at a couple of differential equations later on. So here is an example from last week where we have y prime is this expression in t and y, so t squared plus 7 times t plus 3 over y squared. We can separate this, so we can rewrite it, and here you see that everything with y is on the left side of the equation and everything with t is on the right side of the equation. We integrate them separately, and it's quite easy here because this is just a polynomial in y, so it leads to 1/3 times y to the power 3 plus some constant. Here is a polynomial in t. We also know how to integrate that. It's quite simple. And then we find a solution, and in this solution is still a constant, capital C. And for every capital C for which this expression makes sense, and here that is every value, you can find a different curve. So here I plotted a couple of them using computer software, and you see that you get differently shaped curves for different values of C. So what we have also seen is if you would like to have a unique solution, then you can specify what y is at time 0. So that is on this slide. If you additionally say that y at time 0, so y for t equals 0 should be 3, then we can find the constant and we have a unique solution. So then from the picture that you see here, you pick basically one of the curves, depending on the value of C. So this is what we have seen last week. Now, the last example or application that I would like to show you is on population growth. So what we will look at is a model, and that is called the Verhulst model or logistic model. And what he did is at the turn of the century from the 1800s to the 1900s, he studied the size of the Belgian population. So he wanted to know how many people live in Belgium in the next couple of years. Now, to look at the population size, you would have to take into account that the population of a country cannot simply keep growing. So it doesn't behave like bacterial growth. You won't have exponential growth. The simple reason being is that it costs money for human beings to live. So they need food, they need housing, they need a job, and there is only a limited amount of all that. So what he did was basically expand the bacterial growth model a little bit and try to temper the growth. So for a small population, when there is enough food, enough housing, or no predators and so on, depends a little bit on what type of population you're looking at, you will have that the growth is proportional to the current population size. If you would like to incorporate the fact that you have limited food or limited housing or limited jobs, then what you can do is include an additional term into your differential equation. So you could say, well, let's say that there is a population size capital M, and that is kind of the maximum that the environment can sustain. So if the population size is capital M, it means that there is precisely enough food for everyone, precisely enough jobs, precisely enough houses. Everyone can live happily, but the population shouldn't grow any further because it doesn't fit anymore. And if it shrinks, well, then you have more resources and the population will grow again. So M is called the carrying capacity. And now the idea that Verhulst had was that he was going to look at the differential equation, or well, he was going to say that the population change, y prime of t, is not only proportional to y of t, that's what we have already seen, but now there is an additional term m minus yt. So if there is still space, if y of t is less than capital M, then it can still grow. If y of t would be exactly equal to capital M, you see that you get a 0 here, and it means that the population doesn't change in size anymore. It gets stuck. If the population size would become bigger than capital M, so say you can sustain 1,000 animals somewhere and you have 1,100, then the population size is going to shrink because there is not enough food. So in total, we see that the change of the population in time is proportional to yt times m minus yt. So the first factor here, the yt, is what we had seen for the bacteria last week. And this term here is new, and it expresses that we have limited resources, say limited food. So this is called the logistic growth model. Y prime of t equals k times yt times m minus yt. Now, I would like to solve this equation with you, and we are going to be needing a trick here. That is not clear at this moment in time yet, but I will show that to you. So let me switch to a fresh sheet of paper. Let's see, like this. So the equation that we now have is that y prime of t, so basically the change of the population as a function of time, equals some constant times y of t, and if I just write down this is bacterial growth, but now additional from Verhulst, we have the term capital M minus y of t. So m is a constant, and assume that this constant is known, it's a given constant. And our problem is that we would like to find y as a function of t, given the constants k and m. So let me write this a little bit shorter. dy dt equals k times y times m minus y. This is a minus sign, like this. Now, one thing that is already interesting here is if you see, let me write that in green here, if the population size equals 0, so a special case, let's say that we talk about rabbits, they live somewhere in a wood, we have 0 rabbits. Well, you can immediately see from the differential equation that dy dt is also 0. So if you have no rabbits, there will be no new rabbits. That doesn't come as a surprise. But what you also see from the differential equation is if the population has precisely the carrying capacity, so the maximum amount that can live happily and has enough food, then also dy dt equals m. So y equals 0 and y equals m are kind of special solutions. If at time 0 we would start with this population size, it doesn't change. They are called equilibrium solutions because the population is in equilibrium like this. Now, let's assume that the population is unequal to 0, unequal to m. So assume y is unequal to 0 and y is unequal to capital M. So then I can divide by y and by m minus y, because then I'm not dividing by 0. And then you see that 1 over y times m minus y dy dt equals k. Or if I rewrite it a little bit, you see that 1 over y times m minus y dy equals k times dt. So apparently we have a separable differential equation because I wrote everything with y on the left, everything with t on the right. So we have a separable differential equation. Now, how to solve that? Well, that's what we did last week. So I have to integrate on both sides of the equation. So I can write an integration sign on the left. So the integral 1 over y times m minus y dy equals the integral k dt. Now, the thing on the right is quite easy, because I can immediately write down, well, if I'm integrating with respect to time, with respect to t, k is a constant, so then I find k times t plus some constant. However, on the left, well, I'm going to need a trick there, because this is an integral that you cannot easily see, or it's not clear how to do this. Because we have 1 over y times m minus y. If you like, you could do the multiplication, and then you find my minus y squared. There's going to be a y squared in the denominator, and then if you look in your list of standard integrals, then you will not easily find that. So we need to do something special here. So what can we do? There is a general solution technique, and that general solution technique is called partial fractions, or partial fraction expansion. And it is in variants 2 and 3, but it's a very technical bookkeeping-like integration technique, so we don't do it. Instead, in variant 1, so the calculus that we do here for industrial design and also architecture, we do the arc length and surface area. So, but this one we can with a trick, so I'm going to show you the trick. So what we would like to find is the integral 1 over y times m minus y dy. And what I am going to do is I'm going to rewrite this a little bit. So I'm going to say, well, that is the same as, and then in the numerator, I'm going to write y plus m minus y . And this is almost correct, because if you see what I wrote in the numerator, that's the only part I changed. I wrote y and minus y, so they cancel out, and there is just a capital M there. Well, there used to be a 1, so I'm going to write in front of the integral, I'm going to write 1 over m. And now, so this is the trick that I was talking about. I've just rewritten it in a convenient way. And why is this convenient? So why do I do this? Well, now I can split it into 2 terms. So what I can do now is say, well, this equals 1 over m times the integral. And then I am going to take this y over the denominator as the first bit. So the first bit is going to be y over y times m minus y plus m minus y divided by y times m minus y dy. And why do I do that? Well, as you can see, I can now here strike the y term, and in the second term I can do the m minus y, which means that I can rewrite this as 1 over m times the integral, and then the first one is going to be 1 over m minus y, and the second one is going to be 1 over y dy, like this. And now you hopefully see why I did this, because now I can do the integration, because I have something like 1 over y, or 1 over m minus y, and that's going to be a logarithm. So I know the primitive function here, it's going to be the ln. So for the first one, I am going to find ln absolute value of m minus y. And for the second one, I'm going to find the ln of the absolute value of y. Plus a constant if you like, but we don't need a constant here. And you see that I forgot one minus sign, because the first term, if I differentiate with the chain rule, I get an additional minus 1. So I have to write a minus sign there. Okie doke. Now, let us assume, because I wrote the absolute values here, which is great and you should always do that, but I don't like to carry on. So I'm going to assume now. So assume 0 less than y less than m. So basically I'm assuming that the population size is positive, which makes sense for a population size. And I'm also assuming that it's below the carrying capacity. So then we can write then the integral 1 over y times m minus y dy equals 1 over m, and then we get here minus ln m minus y, so I can forget about the absolute values now, plus ln y. Okay, so that's already quite nice, but we're not done yet. So I'm going to do a bit more. So let me get some more paper here. So let me copy this to the next page. So I'm selecting the integral here. Copy. And paste, like this. Now I'm going to use one of the properties that we have seen for logarithms. If you have the logarithm of something minus the logarithm of something else, then you can take them together. So I can also write this as 1 over m times the ln of y over m minus y. Okay, so that's great. So if you now look at the original differential equation, we separated it and we did the integration on the left and on the right. And what we have found now is that 1 over m times the ln y over m minus y equals k times t plus a constant. Because that's what we found previously when we were integrating over t. So apparently ln y over m minus y equals k times m times t plus some new constant. It is m times c, but I'm not interested to find those sizes, so I just call it c tilde. And now we go basically back to when we were talking about inverse functions, because I can now find what y over m minus y is by taking the exponential function on both sides of the equation. So we have that y over m minus y equals, and let's write that as e to the power k mt plus c tilde. I can split those into e to the power k mt times e to the power c tilde. And e to the power c tilde is a new constant, so I'm going to write that as a times e to the power k mt. And a is an arbitrary integration constant. Okay. So not quite done yet. So you see this is quite a bit of work here, because I'm interested in y of t, and I have y over m minus y. But I can easily solve this equation, because if I multiply both sides of the equation with m minus y, what I find is that apparently y equals m minus y a e to the power k mt. Now I can easily expand this, and I find equals a m e to the power k mt minus a y e to the power k mt. Now there was a lot of letters in here, but just remember that the k and the m are constant, so if you like you can read 2 and 3 for them. And the a is basically the integration constant here. So we have a family of solutions because our solution is going to depend, of course, on the initial population size. It matters how many people we start with if we are going to study the growth of the population. So what we have now is, if I bring this one to the left side of the equation, then what we find, and I need even more paper here. So if I bring it to the left side, I get plus a. So I can take them all together. And what I have then is that the one from the y that we already had on the left-hand side, plus a times this a to the power k t times y. And then what we had in the right, what is left, and that is a times m times e to the power kmt. So almost done here. And what we have now found is that apparently y equals a m e to the power k m t divided by 1 plus a e to the power k m t. So this is the general solution for any moment in time. Now, as we have already seen a couple of times before, we usually specify which member of the family of solutions we are interested in, by saying the size at time 0. So what I would like to do now, I have this general integration constant a in here, which doesn't have any physical meaning. It's just convenient from the mathematical techniques that we used for solving it. So I would like to express the solution in terms of y0. So assume that y equals y0 at time t equals 0. So for instance, we start with 200 people and then we're going to study how the population size is growing in time. So let's plug that in. So then we have that y0 equals a times m exponential of 0 equals 1 divided by 1 plus a, again, times 1 exponential of 0. So apparently y0 times a plus 1 equals a times m. And I would like to kick a out of the formula. So I see y0 times a plus y0 equals a m. Let me continue here. So I find that a times m minus y0 equals y0. So I'm just solving the equation for a. I want an expression for a. And I find that a equals y0 over m minus y0. Okay. That's great. Almost done here. So if I now take this formula here that we had, and I'm going to plug in the expression we just had for a, and then we're done. Then we have the solution to the logistic equation, to the Verhulst model, in its most general form. So let's do that. So then we find that y, oops, let's switch to pen again, that y equals, and we had a times m times the exponential, and a is y0 over m minus y0. So we get y0 m minus y0 times m times e to the power kmt and in the denominator we had a 1 plus a times the exponential, so that becomes 1 plus a, that's y0 over m minus y0 times the exponential kmt. In principle this is fine. You can make it a little bit nicer by multiplying by m minus y0 over m minus y0. So I'm multiplying with 1. And then we find that this equals y0 m e to the power kmt over the 1 becomes m minus y0, and the second terms become y0 e to the power kmt. So this is the solution of the logistic equation. And for the Belgian population at the time that Verhulst was studying this held on for like 5 years in advance, which was a pretty good model, which means that the Belgian government could plan what was coming ahead using this information about the population size. So now this is being used in many more places. So in biology, economics, people use this equation to this day. And we are going to study a little bit more some of the properties. So you could choose a k, m, and y0 and plot this solution. I would like to study what happens here. So if you plug in y0, so note, and this is just checking some properties. If you plug in t equals 0 into the formula, into the solution that we have just found, you find y0 times m times 1 over m minus y0 plus y0. You see in the denominator the minus y0 plus y0 cancel, we just have m. So you see that you find y0, which is what should hold, so that's nice. And what you also see is if you let t go to infinity, well, we have an exponential with a positive number there. So k is a positive number, m is a positive number. So what we get is the limit t is going to infinity, y0 m, and let's divide by e to the power kmt. Then we get here m minus y0 divided by the exponential kmt, and last term is just plus y0. And now if we let t go to infinity, the exponential will go to infinity. So that means that we get y0 times m over y0, because in the denominator the first term is going to 0. So you see that you find m here. So this equals capital M. So apparently if you let time go to infinity, you see that the population size will slowly increase to this equilibrium solution of capital M, the carrying capacity where everybody's happy, has food, has a house, has a job, and so on. So all the resources are sufficient to sustain this, and the population will go to this population size for t going to infinity. So let's see, and that brings me to the last slide on the logistic equation. So here is basically what we have just done, written on the slide. So we have looked at this model here, the logistic differential equation, and we specify the population size at time 0, and then this is the solution that we find. And if you now plot it, so I did that, you find a picture like this. So this is schematically, but on the horizontal axis is t, on the vertical axis is y. If you start with y0, and y0 is a positive number here, it looks almost 0, but it's just above 0. Then you see that in the beginning here, we have exponential growth. And then there is a kind of turning point around here. And then the growth is going to slow down, and you see for t going to infinity, it has a horizontal asymptote, so it assumes the value capital M. So if I write those properties next to it, you see that initially you have almost exponential growth. So when the population is still small, the capital M doesn't have any influence. Then you see that the growth slows down at some point, and then there is a horizontal asymptote y equals m for t going to infinity. There is a question about this model in the chat box, I see. And indeed, you have to know this solution. So either you can choose to recall this solution. I would not advise to do that. But we can also give you the differential equation with some choice for k and for m. And then you would have to try and find the solution here. So you would have to solve it yourself. So you have to know this trick that if you have 1 over y times m minus y, that you can split it. I am going to tell you one way how you can kind of cheat here. As you have seen, when we give your questions during the final exam, it will be like the midterm. So we are going to give you multiple choice answers. So even though you have to give your solutions, we will also ask you to choose from a list of multiple choice answers. So what you could also do is look at the multiple choice answers and look if you recognize the solution there. And then maybe you can check by differentiation that indeed it is the solution to the differential equation. So that is kind of working the other way around. You do not start from the differential equation, solve it to find the solution, but you look at the multiple choice options and see which one of them satisfies the differential equation. Since you know there can only be one solution, there is a unique solution, that is also a valid way to show that you have found the answer. If we give you many options to choose from, it can be quite a bit of work. So it's up to you which way you prefer. So the topics from week 7 here, just to sum up, we have looked at arc length and surface area, which led to nasty integrals. We have looked a little bit at improper integrals, so integrals where something is wrong, and something is wrong can mean that your function is not defined at a point, or maybe it will go to plus or minus infinity, or maybe your integration interval is unlimited, unbounded. That can all happen. And a comparison test to see if such an integral indeed makes sense, gives an answer, does not become infinite. And we will be looking at a couple of questions. So in the questions that you posed me, there are a couple of these improper integrals. So we'll show how to deal with them. Basically, you had to replace, for instance, the limits of your integral with a capital R and then take a limit, right? But we'll see a couple of examples later on. Then we talked about differential equations, studied bacterial growth, Newton's law of cooling, and then we have, in general, looked at separable differential equations and seen one more example, and it was what we just discussed, population growth, the Verhulst model. So that wraps up the week 7 material. After the break, I will be dealing with your questions. So first the questions from the emails that I got, then from the Canvas questions, and if time permits, we will also do some of the extra exercises. And there, as I already said, I will go backwards in time. So I'll start with the topics from week 8 and then go all the way down. We'll see how far we get, giving you examples. In principle, I will do any example that you would like me to do. So if you have further questions, let me know, and maybe not today, but then especially on Wednesday, we still have 2 times 45 minutes. I'll happily solve your questions then. So it is almost time now. So let's have a break at this moment in time. And then at 2:30, we will go and I'll try to answer all the questions that you have posed in the meantime. So let's first have a coffee break and I'll see you in 15 minutes. So let's start again. During the break, there was a question from Jan in the live chat, and she asks, so we can choose between solving the differential equation ourselves or use the formula for logistic growth directly. That is true, so you can learn that by heart. I would advise you, when you write down the solutions during the test, to say, well, I know the solution to the general logistic equation. If the equation is this, and then you write down the general form of the logistic equation, the solution is this. If you write that down, then it's perfectly clear what you're doing. Otherwise, if you just use the analytical solution without writing it down, then the person who is marking your exam may think, well, I'm not sure how she gets this. But if you say, well, I learned it by heart, and you write that down, that's clear. And that holds true in general during the test. There is going to be multiple choice questions where you just have to select the correct answer. And there is going to be open questions. For the open questions, you have to write down how you got to your solution. So you still select from options, but you have to motivate your solution to tell how you got your answer there. Try to be as clear as possible there. So do not only write down equations, but also a couple of words like from this it follows that, or I know that this holds, or I'm going to use integration by substitution. So try to be as clear as possible. It may be immediately clear to you when you write something down what you mean there, but to another person who would solve the question, for instance, in a different way, that may not be clear. So try to be as clear as possible. Writing these little extra bits of stuff that you already know, or what you're thinking, or what is your basically your plan, or which steps you're taking, that can help a lot when someone is trying to see what you're doing and to award points. And as you know, even if you would not have the full answer correctly, you can still have partial credit, so you can still score part of the points if you make clear what you're doing, and it's easy for us to check where you, for instance, made a small computational error. Okay. Having said that, I will now address a couple of the questions that I got by email. So I've seen all your emails by now, and hopefully all of the questions you had will come by here. So let's switch to Me plus iPad. And one of the questions that I got was this. Find or evaluate the integral, and then it goes from 8 to infinity, 1 over x squared, square root 2 plus 1 over x dx. So just for convenience, let's call this thing capital I. That's a bit shorter, and then I don't have to write this whole integral all the time. Now, the very first thing that you should see is that there's an infinity here. So this is an improper integral. So that's the first thing I'm going to note. Improper integral. So I am going to consider capital I with a subscript r, which is going to be the integral from 8 up to r, 1 over x squared, square root 2 plus 1 over x dx. And then later on, I'm going to try and solve this, try to evaluate this integral. And then when I have found something, I will try and let capital R go to plus infinity and see if we get somewhere. Okay. Now, the next thing is we took care of the integral being improper, and now we've got a nice integral. So how can we solve this? So we have basically 3 techniques, right? Does it look like one of the integrals in the table, like a standard integral? Well, it does not. And then we have integration by substitution or integration by parts. And for integration by substitution, what you do is you look at an ugly function. There is an ugly function in there because there is a square root, and square roots are pretty horrible. And it has a 2 plus 1 over x. So if you would try to do substitution, then the substitution you should try is 2 plus 1 over x. And then in the back of your mind, you should already have that if I do u equals 2 plus 1 over x, Then if you differentiate, you find du dx is minus 1 over x squared. So du is minus 1 over x squared dx. And then you see that that works great because we already have the x squared here. So substitution, that's what it's going to be. If substitution would not have worked out, or there would not be a clear function what you should choose there, we would go to integration by parts. But we don't need that here, so let's just do substitution. So integration by substitution. I've already on my scratch paper here worked out what u should be, what du is then. What I'm going to do here, since we have a definite integral, meaning that there is an 8 and an r up there, I'm not looking for any antiderivative, but I'm trying to find a specific integral. Basically, I'm going to get a number here. So I'm going to check what the limits are in u coordinates. So then I don't have to switch back to x anymore. So what I'm going to do is say, well, if x equals 8, then u is going to be 2 plus 1 over 8, which is 16 over 8 plus 1 over 8, 17 over 8. And if x equals capital R, then u is going to be 2 plus 1 over capital R. Okay? So next, our integral, in u is going to be IR is going to be, now we integrate from 17 over 8 up to 2 plus 1 over capital R. And, well, we get 1 over square root of u. I have 1 over x squared dx. So that is going to be times minus du. So I have as a primitive function square root of u, but if I would differentiate this, I would get 1 over 2 times the square root, so minus 2 times the square root of u. And then in between u equals 2 plus 1 over capital R, and u equals 17 over 8. So if you plug in those values, you get minus 2 times the square root 2 plus 1 over capital R. And here we get plus 2 times the square root of 17 over 8. Now, this is the integral where we still have this capital R. So the last thing that you should do now is take the limit of R going to plus infinity. So let's do that on a new piece of paper. So we had that IR equals minus 2 square root 2 plus 1 over capital R plus 2 times square root 17 over 8. And now I, which is what we wanted to find, is the limit capital R going to plus infinity. IR is going to be minus 2 times square root 2. 1 over R will go to 0. Plus 2 times the square root of 17 over 8. If you like, you can write that differently. You could move the 2 here under the square root sign. And then you would get the square root of 17 over 2 after simplification. But this is fine like this. So this is the answer to this integral. So this is how you can do that. Okay. Then the next question that reached me via email is the following integral. let's do a fresh slide. So the integral, oops, that's not going as I wanted it to. The integral of 1 over 6 pi, 2 plus infinity, and then we have sine pi plus 3 over x squared dx. Let me go back to the previous example because there is a question from Amber in the chat box. And that question is here. She asks why I put a minus sign here. The minus sign is because of what we have here. So du dx is minus 1 over x squared, which means that du is minus 1 over x squared dx. So it is basically this minus sign. I multiply both sides of the equation with minus 1 because in my original integral there is plus 1 over x squared. So hopefully that answers your question. And Mirta gives the correct answer, but there's a short delay, so we both agree. That's good. Next one. So this here, again, the first thing that you should see here is that it's an improper integral because the upper limit of the integral is plus infinity. So this is an improper integral. Improper integral. So we consider I capital R is the integral 1 over 6 times pi up to capital R sine pi plus 3 over x squared dx. And this is actually quite a bit like the previous example, because now what we have is we have a complicated function, in this case the sine, and this bit here, so the argument of the sine, whatever you take the sine from, that is a very good candidate to do with substitution. So again, integration by substitution, integration by substitution. So we're going to take u to be pi plus 3 over x, which means that du dx is, well, 3 is just a constant, so I can copy that. If you differentiate 1 over x, you get minus 1 over x squared dx. And again, since there is a x squared here, this is going to work out. Okay, so that helps us. This x squared being there helps this substitution work. If it would not be there, we couldn't manage in this way. We could directly find a primitive, and then it would be something like cosine pi plus 3 over x. So let's see. I have du being equal to minus 3 over x squared dx. Oops, sorry, here I've got a double dx on this slide. Let's remove this one. So du is minus 3 over x squared dx. That's what I put on the second slide. And maybe to make it a little bit more clear this time, I can write this as minus 1/3 du equals 1 over x squared dx, because in my original integral there is a 1 over x squared dx. So if I now replace the integral, so we had, let me copy IR. So we had the integral from 1 over 6 pi up to r sine pi plus 3 over x squared dx. I now want to write this in terms of u, and then I still have to look at the limit. So if you have x being equal to 1 over 6 pi, then u is pi plus 3 over 1 over 6 pi, like this. So apparently that is pi plus 18 pi, which equals 19 pi. And if x equals capital R, then u equals pi plus 3 over capital R. So the integral in terms of u now becomes the integral of 19 pi up to pi plus 3 over r sine of u times minus 1/3 times du. Okay. And then we're basically done. So like I've said times before, you can forget about everything we did so far. Just look upon this as a separate question, and that is not a very difficult integral, because we can just move this minus 1/3 in front of the integral. Primitive of sine equals cosine with a minus sign, so minus times minus becomes plus. And then in between, u equals pi plus 3 over r, and u equals 19 times pi. So almost done now. We have to substitute these limits into the cosine. And then what we find is, let's go to a new slide. So what we find is that this equals 1 over 3 cosine pi plus 3 over capital R minus 1 over 3 cosine 19 pi. Now, if you think that 19 pi is a very big number, just remember that you can subtract 2 pi, right? You can always subtract 2 pi, and if you have the picture of the unit circle, then if you subtract 2 pi, basically you just go once around. And you can do that a number of times. So here I can do that 9 times, which means that I subtract 18 pi. And basically what we have is that this is the same as cosine 19 pi and minus 18 times pi. So that means that I subtracted 2 pi 9 times. So this is the cosine of pi. And pi means that we just go halfway the circle, which means if we start at x equals 1, y equals 0, and then we go half circle, we have an x coordinate of minus 1. And that means that this becomes my plus 1/3 cosine pi plus 3 over r. And then we have plus 1/3. And then finally, I have to take the limit of r going to capital infinity. So capital R going to infinity, sorry. And we have that I equals the limit r going to infinity IR is the limit r is going to infinity 1/3 cosine pi plus 3 over r plus 1/3. If r goes to infinity, 3 over r goes to 0, so the whole thing equals 1/3 cosine pi plus 0 plus 1/3. Cosine pi equals minus 1, so the whole thing is 0. So that is what you find here. And this one is from the online test. So you may have seen a version of this with different numbers because as you know, the online test has questions that you get, well, the same question with different numbers. So you may have had the same one, but then maybe not with the 3 in there, but with some different number. Okay. In week 6, 7, week 7, I think, we talked about arc length and surface area, and I got quite a number of questions on that. So I would like to move to section 5.4 from the book. And this is also a question that someone asked me via email, and I have seen it pop up also, I think, in the question on Canvas. So I would like to go to section 5.4. And then question 8. I guess one of the reasons that I got this multiple times is that the answer in the answer booklet, some people have that, is incorrect. What is asked here is the arc length of y equals 1 over 4 times e to the power 2x plus e to the power minus 2x, and then x ranging from 0 to 1. So what is being asked here is the arc length. And as I told you, the arc length, the integral you get during the exam, that's the integral of the square root of 1 plus f prime squared. So in general, that is going to be a pretty horrible integral. Only for very special functions f, you can actually evaluate this. This e to the power 2x plus e to the power minus 2x is one of them. It's basically the cosine hyperbolic, right? And here you can do that. So let's see how this goes, because many of the other questions on arc length go in a similar way, and you have to see there that you can somehow simplify the integrand, the function you're trying to integrate. That's called the integrand. So let's see. So we have fx is 1 over 4 e to the power 2x plus e to the power minus 2x. I could write this as half cosine hyperbolic 2x, but I prefer to use the exponentials here. Otherwise, you have to know the formula for cosine hyperbolic, sine hyperbolic. So the question is to evaluate this. L, the length of this curve, if you go from 0 to 1. So that is the square root of 1 plus and then f prime x squared dx. So this is the question. Now, first let's compute f prime. So that's 1 over 4, and then we have e to the power 2x, chain rule additional 2, e to the power minus 2x, chain rule a minus 2. So that is going to be 2 over 4, which is 1 over 2, e to the power 2x minus e to the power minus 2x. So if you like, that is something like a sine hyperbolic, but we don't need that, but maybe it helps you. If you square this thing, so if you look at the integral we have to compute, there is an f prime squared in there. So a half squared gives 1 over 4, and then we have e to the power 4x, because e to the power 2x squared, that's e to the power 2x times e to the power 2x, which is e to the power 4x, plus e to the power minus 4x, that's e to the power minus 2x times e to the power minus 2x. And then we have the cross product, and the cross product here is going to be minus 2. So minus 2, let's write it out, e to the power 2x, e to the power minus 2x, that's like the cross product. And as you see, e to the power 2x times e to the power minus 2x, that's 1, right? So this here is 1 over 4 e to the power 4x plus e to the power minus 4x minus 2. Okay. Now, if you look at what we're trying to integrate here, we don't have f prime squared only, but we have f prime squared plus 1. And the plus 1 is going to help us here. So let's see what we get there. So we have that 1 plus f prime x squared. Well, that's 1 plus 1 over 4 e to the power 4x plus e to the power minus 4x minus 2. And what I'm going to do here is write it out in all its steps. So we get 1 plus 1 over 4 e to the power 4x plus 1 over 4 e to the power minus 4x, and then minus 2 over 4, so that's going to be minus a half. And now I'm going to combine the 1 and the minus 1 half. So that's going to be plus 1 half plus 1 over 4 e to the power 4x plus 1 over 4 e to the power minus 4x. And I'm doing it in many steps here. And maybe you would skip some yourself. So this is what we get. E to the power 4x plus e to the power minus 4x plus 2. And now the basic trick or idea, or well, you should have seen this once, is that you can write this as a square again. So this is the 1 over 4 I just copy. But this is e to the power 2x plus now e to the power minus 2x squared. Because if you do the square, so if you expand this, then you get precisely what you have in the line above. And the idea now is that if you do e to the power 2x times e to the power minus 2x, you get a 1 again, and then you get precisely what it says in the previous line. The reason I do that is because we need to integrate the square root of 1 plus f prime x squared. Well, the square root of 1 over 4 is a half. And here we get now, this is all positive, so I can just write it like this. And now we've done all the difficult parts. So now it's basically just a substitution and doing the integration, but it's not going to be very difficult. Because now for the length of the curve, the arc length, that's what's being asked here, what we get is L is now the integral from 0 to 1, the half I can write here, e to the power 2x plus e to the power minus 2x dx. So this is what we finally found for L. And if you do the primitive, you get e to the power 2x minus e to the power minus 2x and then 1 over 4. This is the primitive. X equals 1, x equals 0. So apparently the answer is 1 over 4 e squared minus e to the power minus 2 minus 1 plus 1, which is 1 over 4 e to the power 2 minus e to the power minus 2. So that's how this goes. And you may recall that during the lecture I computed the length of a hanging cable, which was basically the same question as this is. So it's very similar to that. Okay. From the same section in the book, I'm also going to do question 11, which is also in the homework, so maybe you have now a perfect score in the homework, but that's fine. I mean, the main thing is that you score a high mark, hopefully, on the final test. So I'm also going to do section 5.4, question 11. And I'm going to write it in terms of x. So if you look in the book, then the question is in terms of x as a function of y. That's a bit silly here. So I'm just going to write f of x. And then the function is 1 over 8 x to the power 4 plus 1 over 4 times x squared. And then we would like to have the arc length with minus 2 less or equal x less or equal minus 1. So also here, this is a bit silly in the sense that the book chooses to take x negative here, and that has some consequence that we will see in a sec. But the book could also have chosen x to be from 1 to 2, and you would get the same answer because the function has only x squared and x to the power 4 in there. But that's just some extra nastiness by the book. So let's see. If we differentiate, because we are going to compute the arc length, and the arc length has the integral of the square root of 1 plus f prime squared, so we need f prime. So differentiation, 4 over 8 x to the power 3, x to the power minus 2, so we get minus 2 over 4 x to the power minus 3. So what we have is a half x to the power 3 minus 1 over x to the power 3. Now, this looks like a completely different question from the one that we just solved, but there is one similarity, because if I compute the square, because I'm going to be needing that, then you get 1 over 4 x to the power 3 minus 1 over x to the power 3 squared, which is 1 over 4 x to the power 6 plus 1 over x to the power 6. And then there is the cross product of these two, and you get minus 2x to the power 3 times 1 over x to the power 3. So if you look back, this is a bit like the e to the power 2x times e to the power minus 2x that we had before. Because if you have x to the power 3 times 1 over x to the power 3, it's going to be 1 again. So I can grab these together, and I can write this as 1 over 4 x to the power 6 plus 1 over x to the power 6 minus 2. Okay. And if you like, and I'm going to be needing that in a second, so let's write this as 1 over 4x to the power 6 plus 1 over 4 and then x to the power 6 in the denominator, minus 2 over 4 is minus 1/2. In the integral, I need 1 plus f prime squared. So let's take that one. So we have 1 plus f prime x squared is 1 plus what we just found, 1 over 4 x to the power 6 plus 1 over 4 x to the power 6 minus 1/2. And just like before, I'm going to take the 1 and the minus 1/2 together, which is going to give me plus 1/2. Pull out the 1 over 4. And now we get a plus 2, where we had a minus 2 before. And I can write this as a square again. So that's the crucial idea. I need the square root in a second. So I'm going to take the square. I'm going to write this as a square. So this is 1 over 4. And then x to the power 3 now plus 1 over x to the power 3 squared. So with all of these arc length questions or surface area, that's very similar, you have to recognize the square there. And since you know we're asking for arc length, we are giving you very special functions to integrate where you can do this trick, so where you can go to a square. So we have that the square root of 1 plus f prime x squared is now 1/2 times the square root x to the power 3 plus 1 over x to the power 3 squared. And this is the bit, and I'm not sure if you ran against that. If you look at what we were being asked to compute here, so I'm going back now one slide. So here you see that we have x is in between -2 and -1, which means that here, if x is negative, x to the power 3 is negative, 1 over x to the power 3 is negative. So if I do the square root here, I have to include an additional minus sign. That's just some nastiness that the book put there. So this equals -1/2 x to the power 3 plus 1 over x to the power 3, since -2 less x less -1. So since we're going to integrate from -2 to -1, I need to do minus sign here. This is something that we would not put in the exam, because this is clearly just to put you off and to let you make mistakes. Not a very good question if you ask me, but I didn't write the book. Okay, so we're almost done now, because the question was L, the length is the integral from -2 to -1, square root 1 plus f prime x squared dx. So with what we have just found, it's -2 to -1. Here should be a minus sign. And we just found that this equals -1/2 x to the power 3 plus 1 over x to the power 3 dx. And all trick, forget what we have done so far, just look at this integral, it's a simple one. So what we have is -1/2 times, and then we get x to the power 4, 1 over 4, because that's a primitive for x to the power 3. And here we get something with x to the power -2, and then we have to put -1/2 in front of it. And then if we differentiate, we precisely get 1 over x to the power 3. And that in between x equals -1 and x equals -2. So if I plug in those values, then we have -1/2 times, and we get 1 over 4 minus 1/2 minus 16 over 4 plus 1 over 8. And if you compute that, then you will find that this equals 33 over 16. So that concludes this question, where there was a little extra nastiness due to this -2, -1 bit, where we had to put an extra minus sign. Okay. Then I have an additional question from the homework, but now I move to 6.6. So this is from section 6.6 and then question 17a. And that is the integral from 0 to plus infinity 1 over square root x e to the power square root x dx. So the first thing you should always check is if the integrand, so the function you're trying to integrate, this thing here, that is called the integrand, whether it is well behaved or not. And here you see that both at 0 and at plus infinity it is not. And you should also check in between, but in between this thing is fine. But it is improper for two reasons. So the integrand does not exist. At x equals 0. And what you also see is that the integration interval goes to plus infinity. So the upper limit So what we have to do is first rewrite our integral. And since we have two problem areas, we can take a safe point in between 0 and infinity, for instance 1, and split the integral. So what I'm going to do is say, well, the integral we're trying to solve is from 0 to 1. Plus the integral from 1 to infinity. And then, so basically what we do is we first go from 0, then we go to 1, and from 1 we continue on to infinity. And then I can take them apart and split the two problem areas. And I can say, well, let's say that the first integral, this thing here, let's call this I1. The second one here, let's call that I2. And then I'm going to do those separately. So this is just splitting. We've got two problem areas, and I'm just splitting them into two separate integrals. So what you could do is you could say, well, instead of I1, I am going to consider I1a, which is from a to 1 over square root x e square root x dx. And then later on, I'm going to take the limits a going from above to 0, I1a. And similarly, I am going to do I2 of capital R, which is going to be the integral from 1 to capital R, 1 over square root x, e to the power square root x dx. And then I'm going to say that I2 is the limit, R is going to plus infinity, I2 R. And now you can do your basic tricks. So you're going to look for a primitive function, and substitution might be your friend here. Compute these I1 of A, I2 of R, and then take the limits of A going to 0 and R going to infinity. So I'm going to skip those details now, also in view of time. But I'm sure you can manage. If you don't, if you want me to come back to this, ask me and I'll do the rest then on Wednesday. But for now, I would like to leave it at this and then move to the Canvas questions. So I also got a number of questions on Canvas, and I'm also kind of running out of time. So I'm thinking what is wise to do here, because there is a number of questions. And I also see that Lieke posted a question on YouTube in the live chat where she says that the formula for logistic growth in the book is different from the one shown in the first half of the presentation. No, it's not really different. The letter A that the book uses is the population size at 0. So if you look at the formula that you put in the live chat on YouTube, and if you would replace capital A with Y0, so the population size at 0, then you would have the same formula. So it's just that the capital A from the book is not the capital A as I used it in the slides here. Um, in general, a differential equation has a unique solution. So maybe it looks a bit different, but then you can always rewrite it. So if you have a differential equation with an initial condition, so you also specify what the solution is at time 0, then there is only one solution. And maybe you can rewrite it into a different form, but there is one unique solution. Okay. So in principle, it's 3:15. Usually, usually in non-corona times, we would have a Monday afternoon of 4 hours of lecturing, which is quite a lot. So I am happy to continue for a bit. So unlike previous weeks, what I will do now is have another break so you can get some coffee, maybe go to the bathroom if you want to. And then at 15:30, so 3:30, I will do the questions that are currently on Canvas. So I will do the Canvas questions. If you have another appointment, you know that the live stream is saved on YouTube, so you can watch later. Maybe it's a good idea to note down the time point now. But I will be back, so I will have a 15-minute break also to drink a bit of tea. And then I will do the Canvas questions. So some of them more elaborate, some of them shorter, some of them we already seen. But I would like to answer the questions that are currently on Canvas, and then the rest of your questions, if you have any, we'll do on Wednesday. But I'll be back at 3:30, and we have a 15-minute break. So see you in a bit. So let's start again for the diehards, the questions on Canvas. So I'll quickly go through them, probably not in all details, but I'll try to answer all the questions that start from this one. So can you show how to solve the integral? And then it says tangent to the power 4 plus secant to the power 2. So let's switch to my iPad. I wrote down the integral here. First of all, secant, we normally don't use that. So I'm going to rewrite the integrand a little bit. So we have tangent to the power 4x. And what we would write in the test, if we would ask this question, is 1 over cosine squared x. So that is the same as sine to the power 4x over cosine to the power 4x plus 1 over cosine squared x. Now, this is basically trying to rewrite it into something that we can integrate. If you look at what it says here, we have sines, cosines, and 1 over cosine squared. 1 over cosine squared, as you know, is the derivative of the tangent, right? If you differentiate tangent, you get 1 over cosine squared. So probably at some point we will need integration by substitution. I'm just going to rewrite now, but because I have all these sines and cosines, I'm going to write this a little bit shorter, and I'm going to write S for sine, C for cosine, and then try with the rules that we know for sine and cosine to get this a bit simpler. So first, let's give them the same denominator. Then you get S to the power 4 plus C squared over C to the power 4. So that's the same. Now, I know that sine squared, so this is sine squared squared, is the same as 1 minus cosine squared, because sine squared plus cosine squared equals 1. And then if you expand this, we get c to the power 4 plus 1 minus 2c squared plus c squared over c to the power 4. So let's see, that's c to the power 4 plus 1 minus c squared over c to the power 4. 1 minus c squared equals s squared. And now I almost have something that is easier to deal with, because this is the same as 1 plus s squared over c to the power 4. So apparently the whole thing can be written as 1 plus s squared over c squared times 1 over c squared. Yep. Now, and this is something that we need to integrate. Well, so basically just using trigonometric identities, what I have found is that I can write the whole thing as 1 plus tangent squared x times 1 over cosine squared x. And as you see, the one to integrate, that gives just x. And the other one, we have tangent squared times 1 over cosine squared. So you can do that with substitution. If you use the substitution u is tangent of x, then you get the integral of u squared. And you can also do that. And thanks to the 1 over cosine squared dx, you can get a du there. So I'm sure you can do the rest yourself, but this is the main thing that you have to do. No, indeed. So Ilya asks in the live chat about secant. We don't use secant. We don't write that in the test. But this is a question that popped up on Canvas. So we normally wouldn't write that. We would write 1 over cosine instead of secant. So we don't use that those functions. You won't have them in the test. You didn't have them in the midterm. They won't be in the final test. Okay. So let's go back to the questions on Canvas. How do we evaluate the integral x over square root 1 minus x to the power 4? So let's copy that to a slide. Let me copy that. In the meantime, you can read it. So we have the, let's see, we have the integral x over square root 1 minus x to the power 4 dx. So, as I said before, sometimes integration can be kind of nasty because it can be quite hard to see which of the methods you should use there. And well, hopefully this somehow reminds you a little bit. If you have this thing, minus u squared du, this is going to be an arcsign, right? This is in the list of standard integrals. So if you would, for this thing here, do the substitution u equals x squared, then in the denominator you would precisely get square root 1 minus u squared. And we have that du equals 2x dx. So the x here in the numerator together with the dx can give you the du. And then you would get something like an arcsine function. So that is what you should try to do here. This is quite a difficult one to see. So here the substitution is not obvious. And this is a more difficult integral to solve. I immediately admit that this is a more difficult one. So try to do that. If you do not manage, let me know, and then on Wednesday we can go into more detail if you want. So going back to Canvas, it says here, can you please explain the following question? Family of functions given below contains a parameter c. The value of c affects the properties of the functions. Determine what differences, if any, for c being 0, positive or negative. Then determine what the graph would look like for very large positive c's, very large negative c's. So I'm not going to treat this in much detail. Basically, the idea is that we have a function, as you see here, so x to the power 4 plus cx squared. If you pick different values for c, you get different functions, and you can sketch them. So if c equals 0, you have the function x to the power 4. You could plot that. If c equals plus 1, minus 1, you get different functions. If c equals 100, minus 100. The idea is here is just try to see what they look like. So this is not a question you're likely to get at the exam because this is a bit too general and non-specific and hard to grade. So this is not an exam question. So I'm going over it relatively quickly. Also because I know the next question is also related to graphing functions. So what is expected if you have to graph a function? You're not very likely to have that question during the exam, but as we did during the lecture, so what you do is you see where the function is defined, where it possibly has vertical asymptotes, whether it has horizontal asymptotes. You compute the derivative, and you compute where it has extrema, maxima, minima, and you check where it crosses the axis. So what is the value for x equals 0? And when does it cross the horizontal axis? Those are the questions you would typically address if you have to sketch a function. That is a long list, so it's not likely we're going to ask you have to do that during exam. And then there's also the marking bit, which is kind of hard there. So probably you won't get anything like this. But in general, as the recipe I just sketched and as you will find back in the slide. So we did an example during the lectures and there is a recipe there, what you have to check for sketching a function. Can you show how to solve the question use linear approximation? I did that when we were talking about this topic, so maybe you can find that back. And otherwise, the main idea is that you have to compute the tangent line to the sine function at a point close to 9/4. So that value is 2.25. So you pick a value for which you know the sine exactly, that is close to 2.25. And there you would draw the tangent line and use the tangent line as an approximation. And when we were talking about that, so when I discussed it the previous time, we already discussed that normally we would ask you, or we would give the point where you have to find the tangent line. So here it's open, but normally we would say find the linear approximation to the sine function near axis pi/3 or whatever. So we would give the point where you have to find the linear approximation. Here that's open and not very clear. So this is not a very good question in the book. Then there is a question on logistic growth. So the question is, should we be able to derive the formula? Yes, because we don't know partial fractions. True, but you can do the trick here, as I did today. So you write y plus m minus y in the numerator when you're trying to do the separation of variables, or you remember the exact formula, whichever you like best. The problem with the latter is learning the formula by heart, is that you're not going to remember that for a very long time, but maybe you can manage until the exam. Do we have to know the equation for catenary for the exam? We will give that to you. So if there is a question about catenary, we will give you the equation there. You don't have to learn it by heart. When you have to use integration by parts more than once, you would have to choose a u and v multiple times. But these values are different when you choose a second u and v. Is it okay to use a u and v multiple times? Yeah, so you can use the same notation multiple times here. So if you have to do integration by parts a couple of times, you can use u and v also the second time, even though they may differ. It is nice in your written solutions to make clear that you're doing a new integration by parts step. So say, well, we're going to do integration by parts again. Now we choose u equals v equals, so that it's clear that you have different ones. But that's okay. You don't have to give to use new notation there. That's not necessary. So how do we know in an exercise if they mean the arc cosine or 1 over cosine, if they write cosine to the power minus 1? So only the book uses the notation cosine to the power minus 1. In the online test and also the written test that we make for you, we will never use that notation. So only the book has cosine to the power minus 1, and we will always write arc cosine. Do we have to know tabular integration like in 2.7? I checked there in edition 4, since my copy of edition 5 is on the university, and I haven't been there in a while. It is not clear to me what you mean here, so maybe if you can send me a picture and indicate what you precisely mean there, because that wasn't clear to me what you mean by tabular integration. I don't know the term. Could you explain how to solve horrible integral? We already did that, so that's nice. We did it with a different number, I think, but it's the same question basically. So that's great. I'm having trouble with 8 and 11. Well, I did both of those. So that's great. Trouble with 8 and 11. Yeah, same question. In the online test, there was a question. Yeah, this is a bit nasty. So what we have, let me copy the integral to my iPad. So the question we have here is, I'm first going to write it down and then I'll switch screens. The integral from 0 to 5. The numbers are not important, of course, it's just what we're trying to integrate. 1 plus x over the square root 25 minus x squared dx. So let me switch screens. So this one. Now, the idea that you should have here is to split it. So I'm going to delete the 0 and 5 for a sec because that's not very interesting. So I'm going to split it in the integral of 1 over square root 25 minus x squared dx. Hopefully you recognize that. That's in your table. That's like an arcsine. So you can immediately look up what the primitive function is. And then the second one is the integral x over square root 25 minus x squared dx. And this is one that you can do using substitution. So if you do the substitution, u equals 25 minus x squared, then you see that du is minus 2x dx. And since there is an x up here in the numerator, you can do the substitution here. So that's how you can do this. So first split, and then treat them as two separate integrals. One, look up in the table, do a little bit of rewriting, and the other one you can do by substitution. Okay. Back to Canvas. And then we have, how would you calculate this thing here? Well, let's see. What you could do, there was basically two ways to see this. So let me copy the question. So we have the integral. I'm going to make it an indefinite one again. I'm not going to write down the upper and lower limit. So we have x over square root x plus 1 dx. And actually, I'm going to show you two ways to approach this. So method 1 is that you say, well, I see a square root in the denominator of something that is not x, but more complicated than that. So do substitution, u equals x plus 1. Then in the denominator, we get the square root of u, so that's great. But of course, there is still this x in the numerator. And we don't need that for the du, because du equals dx. So what you would have to do then is that you say, well, from this, it follows that x equals u minus 1. So if I call this thing I, then we have that I is the integral, and then I'm just going to replace this with u minus 1 over square root of u du. So that is the first way to do this, and this one you can integrate. I'm sure you can manage. Method 2. Boils down to the same, but what you could say is, well, I have here x over square root x plus 1 dx. Let's write x plus 1 in the numerator, because if I do that, then it gets a little bit simpler. But of course, I cannot simply freely add a plus 1. However, if I also add minus 1, then I haven't changed anything. And now I can split the integral. And I can say, well, this is the integral of x plus 1 over square root x plus 1 minus 1 over square root x plus 1 dx. And if you now read, knowing what we did in method 1, if you would replace x plus 1 with u, you see that you basically have done the same thing. Here, this you can write as square root x plus 1. So you could write the numerator here, x plus 1, as square root x plus 1 times square root x plus 1, and just get rid of this in the denominator. And then you can also find the primitive function. So that's a different way of tackling the question. Okay. So going back to Canvas. In the online test, there was a question that looked like this. The integral from 6 to infinity 1 over a horrible expression. So let's write down the integral here, and then we can easily see, we can see how to do it. So we have the integral. I'm going to just do the integration. I'm not bothering with the limits now. We have 1 over x squared times the square root 2 plus 1 over x dx. So switching to iPad. So this is one for substitution again. So if you look here in the denominator, we have the square root of something horrible. So the standard technique is to do substitution and to say u is 2 plus 1 over x. And then we see that du is minus 1 over x squared dx. And luckily there is a 1 over x squared here, and there is a dx. So they together give you the du. So that's how you could tackle this one. So I'm not giving the full details here, but I'm sure you can manage. And if not, ask me again. And then the last one for now is, could you explain application 1a from chapter 5.4? Well, what you have there is the question. This is also arc length related. So it is, let me see if I can easily insert the question here on my iPad. No, I cannot. I think, 1 second. I am trying to get to this question. Oh, I may have it here. So let's see. Taking a bit too long, sorry about that, but I think I just managed. Yep, so switching to iPad. And here we have the question. So the question here is, two people walk along different paths, starting at the origin. So what is happening here is that we have x-axis, y-axis. And then we have one person who is going along the positive horizontal axis. So he's walking in that direction. So that's person 1. And then we have a second person. And person number 2 walks along the green curve. And that looks something like this. So this curve is y is 2/3 x to the power 3 over 2, and person 2 walks along that path. And what you see, of course, is if you would take a certain point, say S here along the horizontal axis, and you would go up like this, you see that person 2 travels a longer distance. So if you are at x coordinate s, then person 2 has walked a longer distance along the green path than person 1, because person 1 goes along a straight line, and if they have the same speed, then if for the same x coordinate, person 2 has traveled a longer distance. Yeah? And the question in A is, find the point at which one person has walked twice as far as the other. So if indeed you would look at x coordinate s, you would like the green person, person 2, to have traveled 2s. So what you would like is for the arc length, so L, that is from 0 to s, 1 plus f prime x squared dx. And then fx is the path that person 2 is taking. So f of x is 2/3 x to the power 3 over 2. So you compute the derivative, plug it in, square, plus 1, etc. And you would like this then to be, so you can compute this and you find something. And then you would like this to be 2s. Because once it is 2s, it means that person 2 has walked twice as far as person 1. So that is what is being asked here. So I'm not solving the question yet, I'm just telling you what the question is and how you could approach this. So if you can find this arc length, if you can compute it, and then solve for s, that's still a bit of work, then you have solved the problem. So try to do this, and if you have further questions, if you get stuck somewhere, let me know, send me whatever you had and where you got stuck, and then I will have another look, and maybe you'll manage, that would be great. And otherwise, I am going to stop at this moment in time, and I will see you again on Wednesday morning. So I'm perfectly fine to answer questions like this on Wednesday morning. Let me know if you have questions, put them on Canvas. I'm going to start another round now, so let me do that with all of you present here. So going to Canvas again, and then I am going to press the plus sign. Yep, so we've answered all these questions, and another round of questions is starting now. So make sure we have stuff to do on Wednesday. Oh, I should time out. Okay, I will do that in a second. I will round off now. So I wish you a great week. Try to solve as many calculus questions as you can. I know there's also the Dutch Design Week. I'm fully aware of that. But still, Wednesday is our last session. So anything you want me to do, do it before Wednesday. Good luck preparing for the exam, and I'll see you on Wednesday morning. Okay, that's it for now. See you. Bye.